this is Himabindu from the Department of CSIT. So today in this video, I would like to explain about the concept called designing the Turing machine. So in the previous videos, we discussed about what is meant by Turing machine and what are the types of languages we have and what are the types of grammars we have in entirety OCT, theory of computation. So here in this video, Turing machine, how to design a Turing machine, and we will discuss it with the example. So what are the limitations we have for the previous finite automata and regular languages, and now how to overcome this in the Turing machine. So here we will discuss with the examples. Turing machine. So coming to the definition, we already discussed. Let me briefly describe about the definition of Turing machine. So it contains a 7-tuple notation. In that one, a Q is nothing but it is a finite set of states. So we already know that in a finite automata, push-down automata, we already discussed the finite set of states. But that is nothing but how many states required for the construction of a machine. And here the tape T is nothing but the tape alphabet. So here what the additional which is added to the pushdown automata, in the pushdown automata we have the limitations like there is only stack we have, and here in the Turing machines we are following with the tape. So that is also with the infinite memory. So in the pushdown automata, we are using stacks. So for that, to store the values, we are using the stack in the pushdown automata. And in Turing machines, we are using the unlimited and infinite memory tapes. So here the tapes which are used for the storing the elements or alphabets. And here the elements which are stored in the tapes, those are all called as tape alphabets. So those are all represented with the T. T represents the tape alphabets. So those symbols which are placed on the tape which are noted as a tape alphabets. And next B. So B is the blank symbol which is a special symbol which is in the tape. So here we have, if there is a string is there, we have to place the blank symbol. So blank symbol is there in the tape. So if the blank symbol is there, we have to do that. We have to assume that it is a nothing string. There is no string on that place. And next, sigma as usual, we already know that the sigma is nothing but the input alphabets. So the language which contains the alphabets, those are all represented in the sigma. And delta. So delta is nothing but a transition function for the Turing machine. So here in pushdown automata and finite automata, we discussed about the transition. So every transition function is different from machine to machine. And here in the Turing machines are also we have the transition functions. So the transition functions is represented with the delta. And the transition functions which maps Q cross T, that is nothing but the set of states. Q represents the set of states with the T. T is nothing but tape symbol. So we have to give the representation of Q cross T, and also we have to move the left or right. So in the tape we have a head controller, and we have to move from one place to another place. So that is we will discuss in the next slide how to move. And here in the transition functions in the right hand side we have one more option called left or move rights. So based on the transition functions and the tape values, we have to move or left or right. We can move left or right based on the algorithm given by the logical language. We have to move to the left or right. And depending on its present state, so here the tape alphabets which are taken from the tape symbols, we have to take the transitions and we have to move from left to right. And here the Q note is the initial state, and F is the set of finite states. If any state of F is reached in input string is accepted. So as usual, we in the finite automata also, after reading the entire string, whenever it is reaching the mission, whenever reaching the final state, or that is the accept state, so the string is going to be accepted by that mission. So these are all the definitions. These are all the 5-7 tuple notation for the Turing missions. And we'll also discuss about the Turing mission tape. So the tape which contains left and right moves, and in the blanks, and here the alphabets which are there, A, B. So these are all the tape symbols. So these are all the tape symbols. And B is nothing but a blank. So when there is a difference between B and capital B and small b. So if B is there, that is a blank symbol. So this sometimes in some textbooks we also B like this we will write. And here, and these are all the tape input symbols. And the header, this is the finite control, and here we already discussed in the transition functions, we have the tape header is moving to left or right based on the transition. And here this is a finite control, where this finite control can move left or right. So there is a two directions are there based on the transition. This finite controller head can move either left or right. And these are the write and read operations also there in the tape. So after reading the string in the input value, so suppose here 0, 1, 1, 0, 1, 0 is the input string. So to read that string in the tape, we have to replace it with the write, that is a write operation. So this 0 is read and writing the X. After reading 0, we will replace 0 with the X. And after reading 1, we will replace it with the Y. And after reading 0, we will replace it with the X. So this is how read and write operations which are performed in the tape. That is a Turing mission tape. And now we will design the Turing missions with the example. And here is an example of the given language which recognizes the language 0, 1, star 0. So that is nothing but the 0 and the starting 0 and ending 0. In between, how many ones are there in the sense? The 1 star. So the clean closure of 1. So that is nothing but 1 star is nothing but epsilon, comma, 1, comma, 1, 1, 111 and so on. So like this, n number of ones can be there in middle of the zeros, 2 zeros. So like that we have to construct a Turing mission. So suppose this is the Turing mission, and here how to design this. And here we'll take one string in this language. So here the language, we will elaborate this language is 0, 0. Why? Because 1 star is there. So 1 star, first one, it is also having epsilon. So we are no need to take 1. And here 0, 1, 0. And for this one, and 0, 1, 1, 0. And 0, 1, 0, and so on. Like this. This is the language. For this language, we have to construct a Turing mission. And for this one, first step, what we have to do, we have to take the one input string, and we will follow one algorithm, and we will do the left or right moves in the transition in the Turing mission. So we will take one tape. It consists of, we'll take the string, input string is 0, 1, 1, 1, 0. So this is the input string, and we will take that 0 and 1, 1 and 0. So this is the tape symbol. For this, how we will do. So this is a blank, or we can represent with the, this is equal to blank also. So here we have to take this tape, and we will do we will design the Turing mission. And here if we observe, we have the zeros which is followed by n number of ones. So here how to design in the sense, so first we will take the initiation, this is A state. In this one, we have to read this 0 and we have to replace it with the 1. So here 0 is replaced with X and 1 is replaced with Y. And these are the read and write operations. So after performing the read operation of 0, we will replace it with the Y, X. And after reading 1, we have to replace it with the Y. And here we will see, and if the input string which is having 0, so the header is 0, and what we have to do, we have to replace it with the X and we have to move to right. So the header is going to move here. The header is going to be moved here. And here we need to move to another state. So that is nothing but B state. In B state, if how many ones are there, we have to replace it with a 1. So here, how many ones? So here, if the 1 is there, so 1 is replaced with the Y and we have to move to right. And here, so 1 is there and we have to move to right. So again 1 is there, so we will repeat this same step until we will find the 0. And here after this one, after reading this one, we will replace it with the, so I will write this tape after reading. And so 0 is replaced with X and 1 is replaced with Y. And here this 1 also replaced with Y. And here after with this 1, we have to move to left header. Header is moving right and we saw the 0 symbol. So for 0 symbol, if 0 is replaced and 0 is there and we have to replace it with X and we have to move to right. We have to move to right. So here X is replaced here and here we moved, this header is moved to here. And in this case, here we have to take another state. And in this state, we have empty symbol. So that is nothing but blank symbol is there. So whenever in the state after reading the string, whole string, which is reaching the empty string. So after reading this empty string, we have to accept this string. So this 0110 which is belongs to this language and which is recognized by this Turing machine. So here this Turing machine, so blank symbol, this is tau and blank symbol, we have to replace it with the blank symbol again. So here we will replace it with a blank and we have to move to right. So here after reading this blank, after reading this blank symbol also, we are moved to right and which accepts the string, this string. So this is about the Turing machine. So Turing machine designing for the language, it's L is equal to 0, 1 star 0. And now we already know that Turing machines are always deterministic. So deterministic means that in the finite automata we discussed about the Turing machine, we discussed about the deterministic. So what is meant by determinism? So for every state, how many inputs are there, we have to set a path to every input symbol from each and every state. So that is the condition which we are following for the determinism. So here the Turing machines are always, we can say that it is a deterministic. So for this language, how to design a deterministic Turing machine? So for this Turing machine, this we already noted the input symbol. So here for A, to prove that it is a determinism, so for each and every input symbol, we need to set a path, set a transition function where it is going. So we already have the 0 input, and when from the state to A, whenever 1 is given, so in the input string also 0 1 1 0. So here the 1 is there, starting state which is having the 1 which does not belongs to this language. So we can say that does not belongs to this language. So whenever in the state A, initial state is having 1 as an input symbol, it has to go for the result state. So here whenever in the starting here this kind of 1 is there, so 1 is there, we have to replace it with 1 and our right hand side, and we will move to the result state. And we have a 0 and 1, and also having the tape symbol, blank symbol. So whenever the blank symbol is there, blank symbol also, like blank symbol is replaced with blank, and we have to move to right. So for the state A, we set a transitions to 0, 1 and blank. And here also for B, we already have 1 and 0 transitions from B state, and we have to take the empty symbol, that is a blank symbol. So blank is replaced with blank, and we have to move to right, that is in the result direction. And for the C also, we have only blank symbol, and what about 1 and 0 input. So after reading this entire string, whenever we have 0 or 1, we have to move to the, after reading this 1, so 1 is there, 1 or 0, we have to move to the result state. So here this result state, there is nothing but 0. 0 is replaced with 0, and we have to move to our right direction, and that is nothing but the result state. And for 1 also, 1 is replaced with 1, and we have to move to right direction. So this is about the determinism of Turing machine. So this example which belongs to the regular languages. So here there is no need to take this kind of tape for this kind of languages. Why? Because we can easily construct a finite automata and push down automata for this kind of languages. But so here why we are taken this tape, and we infinite length tape we have taken for this kind of language, in the sense to show that how the Turing machine works, and how to replace and how to read and write operations are performed in this construction of Turing machine. So this is the first example which we have designed a Turing machine for the language 0, 1 star 0. And next example, so 0 power n and 1 power n language. So the language which is representing 0 power n and 1 power n. So this kind of language which we can't design a finite automata for this kind of languages. Why? Because there is a n number of zeros and n number of ones. So how many n's are there, how many ones are there, we can't find. So based on the number, we have to set a memory. So memory, it takes in the stack, and in the input symbols we can't store this kind of input elements in the stack. So that for this kind of languages we are taking the Turing machine. So how to design the Turing machine for this kind of languages, we'll see. So and for this one we have to follow this algorithm. So here this only for this kind of language, what is the algorithm to follow this one. And as usual, so if the n is equal to n greater than 0, so we'll take 4, and here n is equal to 4 in the sense the language of one of the string which 0 00 00 11 11. So this is the 8 length. So the string length is 8. For this kind of strings, we will take one of the language string, and we will design the Turing machine for this language. And first of all, we need to draw the tape, and with the 8 length. So 0 0 0 0 11 11. And these are all the blank symbols. So here the blank symbol and so. First step, what we have to do, first whenever 0 is there, we have to read and write it as a X. So here this header is header is 0 and we will replace it with the X. So here we will take one output tape. So what is the output tape for this one? So X is there. And why? Because X is there, and we will follow this algorithm and we will construct the Turing machine as well as. And here 0 is replaced with X. So here the language which is minimum length. So here n greater than 0, that is nothing but, so it has 1. N is equal to 1 onwards we will write 4. Suppose n is equal to 1, 0, 1 is the string, and n is equal to 2, 0, 0, 1, 1, and n is equal to 3, 0, 0, 0, 1, 1, and n is equal to 4, 0, 0, 0, 1, 1, 1. So like this the language contains the string. So here in this one we have taken this string, and first thing is 0, 0 is followed by 1. So n number of zeros is followed by n number of 1. So here the logic behind this one, so 0 is followed by 1. So here for this kind of thing, first 0 is replaced with X. And after that, how many zeros are there? We have to skip that and we have to move to the first one. So here move right to first one. So here we need to skip all this, not skip, we have to replace 0 with 0 and 0 until we find the first one. So first one we have to find out and we have to replace it with the, so here 0, 0 and 0 and Y. Y is replaced here. And after that, if there is no 1 here, we have directly reject this, directly we go for the result. And after this one, change 1 to Y. So Y is changed and this header move left to leftmost 0. So leftmost 0 is nothing but here the header is moving from 1 to leftmost. So here this is the leftmost 0. Why? Because here this is the leftmost 0. Why? Because this the first 0 is already replaced with X. So the leftmost 0 now is here, this one. And here we will replace it with the, so already X is there and we will replace it with the leftmost 0 and we will replace it with the X. So we have to repeat this one to this step. So X is replaced, and when how many zeros are there, we have to skip those zeros until we find the one more 1. So here the 1 is moved and here this we have to write this one. And here this 1, so this header is moved to this one. So here the 1 is replaced and Y is replaced. And again we have to move to the leftmost 0. And here this leftmost 0 which is replaced with X. And here after replacing the 0 with X, we have to move this header to rightmost 1. So rightmost 1 is here and we have to replace it with Y. So this is the rightmost symbol and here this 1 is there. And again this we have to move to the leftmost 0 and here leftmost 0 is replaced with X, and this after this one we have to move to rightmost 1. So this 1 is also replaced with Y. And here finally we reached the blank symbol. So blank symbol, whenever we are reaching the blank symbol, we have to move to the accept state. So this is how we designed the Turing machine for this algorithm. And now we will design in the machine how many states and how many input symbols are there. We have to follow those input symbols and how to move from left to right in the direction form. And we'll design that. So here is the Turing machine. So in this one, and here the Turing machine, this initial state is a transition. So transition function A, transition state which is A, and we have to move to 0. Whenever the A is having the 0 input symbol, we have to replace it with X, and we have to move to right direction. So, and here in the right direction, whenever we saw the 0, whenever we saw the 0, we have to replace it with a 0 and we have to move to right. And here after this one, for this one and 0, and we will find, whenever we find 1, we have to replace it with Y and we have to move to left direction. And here this is the C. And here after this one, whenever we find the 0 is there, and we will replace it with the R symbol. So this and here Y, so Y is there, and here in this case, so here like this. And here this Y is replaced with Y, and or we have to move to right direction. And here also, if we have 0 input symbol and we have to replace it with the 0. So here this one. After this one, after 1 is replaced with Y, we have to move to left direction. In the left direction also, we have to follow like this. So here 0 is there, so Y is there. So here after this Y is replaced and 0 is there, we have to move to left direction. So in the left direction we find 0, we have to replace it with the 0 and we have to move to left direction. And here whenever the Y is there, we have to replace it with Y and we have to move to the left direction. And here after this one, whenever we reaches the string 0, whenever we reaches the X, so here the X is there. After this one, we find any X value, we have to replace it with X and we have to move to right direction. And here, and finally, whenever we reaches the so here after reading this entire thing, whenever the Y is there, so after reading the Y, we have to move to the right direction. So here right direction, Y tends to Y, and we have to Y tends to Y and in the right direction. So this is D, and here right direction. So how many Y's are there? We have to repeat those Y. We will replace it with Y and we have to move to right direction. And the header finally, whichever finally we reaches the blank symbol. So here the blank symbol is there. We have to accept the string. So I accept this string. And here the blank symbol also, and here the blank symbol which is replaced with the blank, and we have to move to right direction. And here also after reading this one blank symbol, so blank symbol is there. So after reading entire Y, whenever we reaches the blank symbol, we have to replace it with the blank symbol and we move to the left or right direction. So here in the direction we saw the accept state. So here like this we constructed a Turing machine, and we will also check whether this whether this Turing machine is deriving the strings, stimulating the string, the given language string or not, we'll check. So we will take this string 000 and 111. So here the 000. So we'll do this 000, 000, double. and blank symbol. So here we, according to the Turing mission, we will move. And here the first input string is the header is 0, and we have what we have to do. We have to replace it with X. So X, and after this one we have to move to in the right direction. So how many zeros are there? We have to skip all those zeros, and whenever we find the 1, we have to replace it with Y, and remaining ones are will be replaced with the same. And here after this one, whenever we reaches the 0, the leftmost 0 is there. So here after this Y, so Y is replaced, Y is there, and we move to left direction. So in the left direction, how many zeros are there? So how many zeros are appears? We have to move to the left direction, and if we saw the leftmost 0, we have to replace it with the X. So here the left, so X is there, so X is there, and here X is replaced, and this again we have to move to right direction, and whenever we saw the 0, we have to replace it with X, and we have to move to right direction. So 0 is there, and we have to find the one more 1, and we will replace it with 1 Y and 1 B. And again this step is repeated, and we will follow this, and in the from right to left we are taking, whenever the X is there we have to replace those X, and in the left right direction we have to move, and here 0 is replaced with X, and so after the X is replaced we move to the next input symbol of 1. So we have to find this one, and this Y and Y, 1 is replaced with Y, and when after this one we reached the blank symbol. So here the blank symbol is reached, so here we have to accept the string. So accept the string. So like this we have designed the Turing mission for the language 0 power n and 1 power n. So these are all the Turing mission designing. So here we discussed with the 2 examples. So here this is the tape which contains the memory, infinite memory, which we can replace with the input symbols with the other tape symbols. So this is about the designing Turing missions. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.